It's certainly my pleasure to welcome our speaker today. Gary Davis is the CTS and Richard Braun Chair in Transportation Engineering, faculty member in the Civil Engineering and Geoengineering program. His research is in all sorts of areas that are of quite interest, in the area of causal inference and impact assessments in traffic safety, the application of accident investigations and reconstruction methods for dealing with traffic engineering situations, the use of Bayesian statistical methods in traffic and transportation engineering, and the applications of optimization methods to problems in traffic engineering. Professor Davis received his PhD in civil engineering from the University of Washington, but I should point out that he received a bachelor's and master's degree in experimental psychology before he went on back to get that civil engineering PhD. He was in 86 to 87. He was a visiting researcher at the Royal Institute of Technology in Stockholm, Sweden. One interesting sideline of Professor Davis's research, he's been very interested in how did surveyors and Native Americans collaborate on scientific methods back in the 18th and 19th century, and has been studying surveyors of that period, David Thompson and Joseph Nicolet, and think about it, how did people develop maps centuries ago? And so that's another expertise of our speaker this morning. So without further ado, Professor Davis, and I'm going to let you read the title. It's a long one. Thank you.
All right. Thank you, Max. All right, so we'll talk about something a little more contemporary, okay, than the 18th and 19th centuries here today. I'll read the title once. Okay, Bayesian Estimation of Drivers' Gap Selections and Reaction Times on Left-Turning Crashes from Event Data Recorder Pre-Crash Data here. Let me start out by defining some of the terms turning up in here. So Bayesian estimation, that was a big one. Okay, what we're going to be talking about is crash reconstruction, which is trying to figure out how and why crashes, individual crashes, okay, happen to occur. That's generally a branch of forensic science, okay, and so we're starting to talk about, forensic science. And a recurring and unavoidable topic, okay, if you follow this, is quantifying uncertainty in forensic science. And there are a number of areas where that still seems to be a vexing question, for instance. Let me read a quote from a classic crash reconstruction text. Whenever measurements are made and whenever calculations are based on experimental data, a level of uncertainty exists. Okay, we can't get away, okay, from uncertainty. Dennis Lindley, the late Dennis Lindley, I guess he left us just a couple years ago, fairly famous statistician, okay, and probability theorist, okay, working in what's called Bayesian inference. He wrote a paper on uncertainty in forensic science just about the time I was starting out, okay, as an assistant professor. And Professor Lindley says the only sensible way to handle uncertainty is by means of probability. Another probability is a logic for reasoning about uncertainty. And we assess the weight of evidence using a theorem from probability called Bayes' theorem here. And Professor Lindley also noted two different kinds of problems, okay, in forensic science. Okay, type 1 is identifying a criminal. Okay, this is what this kind of classic DNA analysis does here. Type 2, quoting, we got the case of a motorist charged with dangerous driving. Okay, here the possible criminal is known. All right, what is in doubt is whether or not there was a crime. In other words, where the circumstances of this event meet some sort of threshold so that we would call it criminal or civil liability. All right, Professor Lindley said he wasn't going to say much about type 2. He focused on type 1 in his paper. Unfortunately, it's type 2, okay, that we have to worry about, okay? And so, to some extent, you can think of this talk as a kind of a protracted attack on how to deal with type 2 sorts of problems here. So let me just introduce this idea of Bayes' theorem, okay, which is a big one here. I got a picture of the Reverend Thomas Bayes. This may or may not actually be a picture of him. Historians quibble on this, okay, to some extent, but he gets credit, okay, for proving this result. And a way to think about Bayes' theorem, it's a way of updating your assessment of uncertainty. And so what's going on here is we think here we got some events that we're interested in. Okay, G says the suspect is guilty. Okay, G squiggle means the suspect is not guilty. Okay, those are the questions of interest. We have some evidence, all right, relevant to this. And we're also able to compute the probabilities of getting that evidence if the suspect is guilty. You know, like if he really did commit the crime, what's the probability his DNA would match the DNA at the crime scene? And then the probability of getting the evidence, okay, if he's not guilty. Okay, if it was just random, okay, well maybe the probability of a match would be, 1 in 200 million or something like that, like you see cited here. And so we start out with a prior assessment, okay, of the question of interest, whether he's guilty or not, assign probabilities to it. We get our evidence, and then we update our assessments based on the evidence using good old Bayes' theorem here. This is the version that we usually see it in introductory statistics class. All right, what carries over to more sophisticated and complicated situations, okay, that we're going to run into here. So the why I like Bayesian crash reconstruction is when we're trying to look and see what happened in a crash, okay, we've got a number of sources of information. Okay, one of them is physical knowledge. Okay, crashes are physical events. Okay, whatever happened there, our description's got to be consistent with physical plausibility. In addition, we'll usually have measurements on the particular event. And then we'll often have some expert opinion about what's likely to have happened here. And we're looking for a method of combining, okay, these three sources of inputs into one common framework. And Bayesian approach, okay, allows us to do that, okay, in a fairly straightforward manner. Okay, so there's Bayesian estimation. The other big one is event data recorder. Okay, what's an event data recorder? There's one, or a picture of one. Okay, it's down there in between the driver and passenger seats, down in the floor of this vehicle here. I had to cut away the rug, okay, to get at it here. What this actually is, it's not the event data recorder, it's the airbag control module. All right, so it's a gadget. It's got some accelerometers. It's got a processor. The processor is monitoring the accelerometers, okay, constantly trying to decide whether it needs to set off your airbags or not. In addition, though, to what the accelerometers will do, okay, most of them, okay, and pretty much all of them now, are also monitoring information off the vehicle's network and storing that in kind of a rolling buffer so that if the module decides that we need to set off the airbags, what it can do is go pull that information out of that buffer and put it into some sort of permanent storage. And then it is possible, after the event, okay, to insert the appropriate cable here and with the appropriate software, download that information and have it available for, well, whatever you want to do, I guess. All right, so here's kind of two kinds of information you get out of these event data recorders. Okay, one of them is a crash pulse. In other words, a reproduction of the change in speed during the actual physical time the vehicles are in contact and crashing here. All right, and so the kind of hard to see, but the time scale down here is milliseconds. Okay, so we're talking about an event that happened over, about -70 to 10, maybe 80 milliseconds, okay, 0.08 seconds, and a change in speed, okay, of looks like around 8 miles an hour. All right, so over that 0.08 seconds, the vehicle's speed changed, okay, by about 8 miles an hour here. All right, this change is what the crash reconstruction is called delta V. Okay, we'll see that term again. So one of the things we can get from this, okay, EDR data, all right, are delta Vs. And as I mentioned before, a lot of these things are monitoring the vehicle's network and saving information about what's going on. And so another source of what happened type information, all right, is this pre-crash data here. All right, and so here AE means algorithm enable. That's the moment at which the airbag control module thinks there's something going on and it needs to start deciding whether to set off the airbag or not. And so we got -1, 2, 3, 4, 5 seconds before that. And we have vehicle speeds, okay, essentially it's speedometer speeds. We have engine RPMs, we have percent throttles, and we have whether the brake circuit, okay, switch is closed or not. So looking at that, we can say, well, traveling around about 40, 45 miles an hour, and then about, what does it look like? 2 seconds before algorithm enable, the driver gets his or her foot on the brake, starts to slow down, engine speed goes down, throttle goes down, and then the collision occurs somewhere in here. So we can get a partial story, what was happening, okay, before that crash event. Okay, so driver behavior and crash causation. We've probably all seen this sort of statistic here from the tri-level study done back in the 1970s in Indiana here, where they looked at a set of crashes that were investigated and decided in 93% of them some sort of human error was causal. In 34%, there was some sort of environmental situation, road defect or whatever. And in 13%, there was some sort of vehicle defect. Okay, you hear that. 90% of crashes are caused by humans. Okay, we've all heard that kind of stuff. Okay, that goes back, okay, to this sort of study. Hot topic right now, safety impact of automated vehicles. I think we can say with confidence that a fleet of 100% fully automated vehicles will eliminate human driver error as a cause of crashes. Are we all willing to agree to that anyway? Okay, whether it'll eliminate crashes or not, that's another question completely, okay? Partly because it's hard to know exactly what humans do when they're involved in crashes. Some limited work along this line has been done over in Europe, looking at essentially reconstructed crashes, both of them from GIDAS, means German in-depth accident system, this database of reconstructed crashes in Germany. One of them looked at the ability of a partial automation to prevent pedestrian crashes, and another more recent one, partial automation to look at preventing left turn crashes. So there's a little limited work, okay? Essentially what you do is you take the investigated crash, you imagine what the automated system would have done instead, and you look and see if the crash still occurs. Okay, well, what we've been working on here is trying to put together, okay, a set of investigated left turn crashes so that we can do similar things. And what we've been looking at is a crash database that the National Highway Traffic Safety Administration puts together. And this is an example, okay, from this NHTSA database. This involved a left turn crash between a Chevy Malibu, which was, see if I can get them right, here, and then attempting to turn left, and a Chevy Blazer, all right, coming this way, okay, and they collided here. And so we've been mining this database, looking for events where we've got pre-crash data from both the vehicles that are involved, all right? And that doesn't happen as often as we would like, although it's becoming more frequent, okay, as more and more manufacturers get on board, okay, with this EDR technology here. So this is the event. What we want to do is for each of these, estimate a set of what we call crash elements. And a way to think about these, this is the minimum amount of stuff we would need in order to simulate whether or not the crash occurs. So we need to know stuff like, all right, the time between when the turning driver starts the turn and they reach the conflict point. The speed of the opposing vehicle, the distance of the opposing vehicle, opposing driver's reaction time, and the opposing driver's braking deceleration. All right, if I happen to know those 5 numbers, I can then say, well, if this person had reacted in a half a second instead of 2 seconds, would the crash still have been prevented? So this is kind of a minimal description of the event that would allow us to do this sort of simulation. All right, well, for this crash we were just looking at, NHTSA's identifier is 2012-12-044. That means it occurred in the year 2012 in NHTSA's sampling district number 12, and it was the 44th crash, okay, in that list here. All right, so for the Malibu, the turning vehicle, we've got 5 seconds of pre-crash data. For the Blazer, okay, the opposing vehicle, we've got 5 seconds of pre-crash data. And so what we want to do is take this and use it to estimate those 5 elements, all right, that we're shooting for here. So you can start out with kind of a real naive approach. Just plot this stuff. Here's a plot of the Blazer's speed, time -1, -2, -3, -4, -5 here. Taking the speeds, we can integrate them and get its rough positions at those times. Here's the brake for the Blazer, whether it's either on or off. And then here we've got the throttle for the Malibu here. So what this tells us is that, well, somewhere between -4 and -3 before the event, that's when the Malibu driver started the left turn. Somewhere between -3 and -2, all right, the driver of the Blazer got his or her foot on the brake, slowed down, all right, but was not able to prevent the crash. All right, so we got some rough ideas. How far away were we? How fast were we going? What was the rough reaction time? All right, we can, even from this crude thing, we can make some claims or try to make some claims. All right, here's the issues with that, though. Time 0 is unknown. In other words, that -1 is not necessarily 1 second before the collision. Okay, all we know for GM-type event data recorders is the collision happened somewhere roughly between -1 and 0. Okay, having to do with the way that the pre-crash data are stored and then updated, okay, in their buffer here. So -1 isn't necessarily 1 second before impact. All right, we got our sampling rate issue. Okay, we're only sampling every 1 second, so we don't know what happened in between those times. Synchronizing the EDRs for the 2 vehicles. All right, -1 for the first vehicle might not be the same as -1 for the second. Okay. And then finally, measurement error. These aren't perfect, okay? All the research that's done in this sort of area indicates that the stuff we get from these EDRs has a certain amount of measurement error. All right, so here's our general proposed solution. We use a method called planar impact to estimate vehicle speeds, okay, at the moment of impact here. All right. We will then attempt to use these impact speeds to synchronize the EDRs. And then from the synchronized EDRs, we reconstruct the vehicle's trajectories just before the crash. From the reconstructed trajectories, we estimate our crash elements. And then we use Markov chain Monte Carlo, a computational tool, to do this in a Bayesian sort of way. All right. Well, before looking at how this works, okay, one of the things, and we're currently working on this, all right, is at least some partial validation using instrumented crash tests. All right, so here, this is a test that was done at the 2016 ARC CSI conference here, and I subscribe to a magazine, and one of the things that comes out in this magazine is a DVD, okay, that has data from these crash tests in it, including these videos. So let's take a look at this. We can get it to work here. All right. So we got a Crown Victoria and a Volkswagen Passat doing a head-on crash. Bam, okay? These were instrumented so that, among other things, we know roughly what the speeds at impact were, okay? And so what we want to do is go back and take the kind of information we'd have in a crash reconstruction and estimate those, and then compare. So what kind of information do we have? We got crush profiles, okay, from the vehicles. We have information from the event data recorder in the Crown Vic. Got no information from the Passat. We can get the exit directions for these vehicles and planar impact. Basically, it's a rigid body model, okay, that says, okay, they hit, they moved out at a certain direction. All right, can we infer what the speeds at impact were? Okay, it's kind of complicated, all right, but can be done here. And what we got, all right, was this here. This is our Bayesian posterior distribution for the Crown Vic's impact speed. Roughly somewhere between, it looks like 35 and, call it 55 kilometers per hour. And then this C here is roughly where the measured instrumentation impact speed was. And so our Bayesian posterior is pretty much centered over the true value here with a not unreasonable range of uncertainty. For the Passat, going a little faster, here's the posterior distribution. All right, here's its measured impact speed, and again, didn't do too badly here. All right, so we at least got some confidence, okay, that this planar impact method, okay, isn't totally off base. All right, here's another test. And let me point out some stuff here. So this is a Chevy Malibu and a Mazda 3. We're in the Chevy Malibu looking forward here. The Mazda is down here. And what I want to point out here is that in this screen, all right, we have time and speed, okay? This is provided, okay, by the race logic V-box, okay? So that's part of the instrumentation. So over time, we can see how the speed of this thing changes. And so what we can imagine doing is extracting speed versus time for this as kind of our ground truth, and then comparing it to what the event data recorder reconstruction would give us here. So let's take a look at this one. Okay, got it. I think that had a human driver in it too. Okay. Oops, I want to play it again. There we go. All right, so what do we want to do? We want to construct a ground truth Malibu trajectory using the V-box data, estimate the impact speed using planar impact, use the impact speed and the EDR data, all right, to estimate speeds and positions, and then compare these. So we got some EDR data from the Malibu. Okay, it was a General Motors system. Okay, and so we got kind of this classic -1, -2, -3, -4, -5 type stuff here, including speeds, braking, throttle, okay, that sort of stuff. And so here's a plot. Okay, the red is the speed from the V-box, and then the blue is the speeds from the event data recorder. And we got some error bars on the event data recorder speeds because they are to some extent certain. And then here's our collision speed, okay, a fair amount of uncertainty, okay, regarding that. All right, but I guess the main thing to kind of notice is that we seem to be catching, okay, these V-box ground truth speeds without, too much problem. Okay, there's uncertainty, but our ground truth speeds are falling at least within, okay, the uncertainty intervals. And you can kind of see that place where the Malibu goes up and over the ramp, okay, and bouncing, okay, occurring right around here. So again, since our estimation of the reaction times, braking rates, and speeds are based on these trajectories. Again, we decided this, it's looking reasonable. And this is kind of the similar thing for the Malibu's position, okay, prior to crash, made from integrating the speeds. And again, we seem to be not doing all that badly, okay, as far as estimating the position. Okay, so now we'll go back to what the original goal, all right, was, which was looking at these NHTSA crashes. Okay, so we're back to 212.12-044 here, the Malibu and the Blazer. NHTSA usually does a pretty good job, okay, investigating these crashes. There were a lot of photographs. They measured the crush, okay, the deformation, okay, the vehicle suffered, and reported that to us here. Similarly, we got that crush information for the Blazer, event data recorder from the Malibu, and for the Malibu, this is what they call the deployment event, which means the airbag went off. Since it was a deployment event, we not only have this pre-crash data, all right, but we've got a crash pulse as well. For the Blazer, this was a non-deployment event. In other words, the Blazer didn't hit the Malibu hard enough to set off the airbags. It basically hit it and knocked it off to the side and kept on going here. So what happened was we got enough deceleration to kick in the airbag control module's algorithm. So it decided, okay, something's happening. I'll save this information. But it never reached the threshold to set off the airbags. Okay, so we don't have a crash pulse, but we do have pre-crash data here. All right, and so our estimate of the Blazer's impact speed, fairly wide range because we were allowing for a fair amount of uncertainty in a lot of the measurements that went into that. All right, but somewhere around about 30 miles an hour, okay, is what we think the speed at impact was. And so here finally, all right, I won't go into the details of how our Bayesian algorithm works, all right, but what we've got here are our estimates of those 5 crash elements, all right. So turning vehicle time to collision, the time between when the turning driver started moving and when the collision occurred. Approximately 3 seconds, but with a plausible range between 2.2 and 3.8. Opposing vehicle, the Blazer's initial speed in feet per second, about 65 feet per second, okay, but plausibly within about 61 and 68. Opposing vehicle initial distance, about 170 feet, between 118 and 224. The apparent time gap, which is basically just going to be distance divided by speed. What did this gap look like to the left turning driver when he or she decided to accept it? Well, our mean estimate, 2.6 seconds, okay, somewhere between 1.8 and 3.6, okay, with fairly high probability. That's a very short gap, which is what you'd expect since this is a crash that occurred here, okay? Generally, when we do gap acceptance studies, we rarely see drivers, okay, accepting gaps this short. Opposing driver reaction time, around 1 second, okay, between negative 0.5 and 2.3. This would suggest that the evidence is at least not completely inconsistent with the opposing driver starting to slow down before the Malibu started the left turn. That's not bad. Okay, 1 second is fairly typical reaction time. It doesn't look like we could blame really slow reaction on the part of the Blazer as a cause of this crash. And the deceleration rate, okay, after he got his foot on the brake, around 14.5 feet per second squared, around be about what? 0.4, 0.5 G, somewhere in that neighborhood, which is solid braking, but not really emergency panicky braking. Okay, so let me look at a couple more. This is NAS CDS case 2013-7434, so it happened in 2013 in sampling District 74. It was the 34th event that they investigated. a Chevy Lumina versus a Blazer. You'll notice that both of these cases had General Motors vehicles involved in them. Okay, that's partly because GM was first on board, okay, with making event data recorder available here. And our research into the literature, we're more confident with the error properties of GM EDRs than they are with some of the more recent ones. So our initial focus was just on cases where both vehicles are GM vehicles. Okay, so two GM vehicles colliding here. Here's our left turner. Here's our opposing vehicle. Pre-crash data for this one. All right, well, the Blazer, the opposing vehicle, okay, traveling about 50 miles an hour here. That's interesting. Let me go back one. Oops. Speed limit here, 56 kilometers per hour. All right, what's that in miles per hour? About 35 miles an hour? Okay. All right, so going a little fast. Okay. Brake is on and then off and then back on again. The Lumina, the one that's turning left, okay, originally not moving too fast, and then somewhere around about -4, -3, okay, decides to go for it here and leaves the brake off all the time. Here, clearly we're seeing something happening, okay, got our foot back on the brake, okay, starting to slow down, okay, but again, since these are crashes, okay, the crash occurred here. Well, let's look at our Bayes estimates, okay, for this one. Turning vehicle time to collision, 2.8, between 2 and 4 roughly. Opposing vehicle initial speed in feet per second, around about 75, okay, between 72 and 74. Opposing vehicle initial distance, between about 120 and 260. The gap, apparent gap, okay, 1.7 to 3.4. So again, we've got a fairly short gap, okay, so short gap seems to be an issue here. Driver reaction time, about 1.4 seconds, between 0.5 and 2.4. So again, not atypically slow. There was a reaction here. And opposing driver deceleration, well, it looks like when he did get his foot on the brake, he tried to slow down pretty good. Okay, we're almost 1G here, okay, for this upper bound here, for instance. So he definitely saw something happening, all right, but again, wasn't able to prevent the event here. All right, one more. Okay, this is NAS CDS case 2013-12-111. A Chevy Captiva, okay, versus an Impala. The pre-crash data here, okay, the Impala is the opposing vehicle, the Captiva is the turning vehicle. Something that's not displayed here because I couldn't get it to fit, all right, but the Captiva actually provides pre-crash data every half a second instead of every 1 second. Okay, and I dinked around trying to get that to fit on here, and I couldn't get that table to fit, so I left it out. But we've got data at a higher resolution for the Captiva, okay, than we have, okay, for the Impala, for instance. That half-second resolution is what NHTSA, let's see, in vehicles that came out in September 2012 or later, okay, there's some conditions that the event data recorders are supposed to satisfy. NHTSA doesn't require that manufacturers have an event data recorder, but if they do, there are some conditions for it. One of them is they should provide information, pre-crash data at least this half a second resolution here. Another is that this data be accessible by some sort of publicly available tool, okay? So for what we can kind of expect, okay, as time goes on, we'll have more, more vehicles where we can get this sort of data at a higher resolution, okay, than what we've been wrestling with, okay, in the past here. All right, So what do we got here? The Impala traveling around about 30, 35 miles an hour. The Captiva making the turn here. And it looks like we got our brake on and then start our turn about at -2 here. The driver of the Impala gets his foot on the brake or her foot on the brake here about -1 here, for instance. And so what can we do with this? All right, well, here's our elements. What do we think happened? Turning vehicle time, around, begin between 2 and 3 seconds. Opposing vehicle initial speed, around 50 feet per second. Distance, 94 to 136. So this is noticeably closer than the other two we saw here. Parent gap, again, 1.9 to 2.8 here. A bit shorter, okay, than some that we've seen. Opposing driver reaction time, well, around 1.6, between 0.9 and 2.3. So again, not unreasonable reaction here. And deceleration, well, hard to pin down, okay, but not insubstantial here. Okay, so what have we learned, okay, from all this stuff? Well, this estimation is feasible. We can do it, okay? We showed we could do it, okay, and done it numerous times. All right, but we got non-trivial uncertainties still there, okay? And we look at these ranges here, okay, it would be nice to be able to shrink those a bit, all right? So still fairly non-trivial uncertainties as far as pinning down these numbers here. Where are we at? Precise characterization of individual events, okay, it continues to be difficult. It would be kind of rough to say, you know, one driver was at fault and the other wasn't, unless we knew something about the traffic signal control or something like that, okay, operating at that time. At least in terms of their behaviors, well, the turning driver seems to accept a fairly short gap for whatever reason. The opposing drivers do react reasonably, okay, but this combination of short gap and normal driving just isn't sufficient, okay, to allow reasonable behavior to prevent the crash. That seems to be roughly what's going on. But we got a range of uncertainty here. If we had a large sample, okay, we could probably do some statistical analyses and look at overall general effects. But I'd be cautious about getting too carried away making strong claims about any particular individual event, okay, based on this sort of stuff. Okay. Each of these crashes, all right, had unique features to it. And informed judgment was needed in applying the cases, okay? This is not ready for naive algorithmic sort of application, okay? It takes some experienced judgment to make some decisions, okay, about carrying out these reconstructions. Okay, so what do they say? Facts plus opinion is still opinion. Okay, this is highly quantified, but nonetheless, highly quantified opinion is what's coming out here. In a sense, it's my expert opinion on what happened. Okay, I would not go so far as to say that these are all incontrovertible facts. All right, comparing case 2013-1211, where we had pre-crash data at the half a second rate, okay, the uncertainty ranges were a bit shorter, okay, suggesting that as higher resolution EDR data becomes available, okay, we should be able to get a little bit more precise in terms of what we're doing here. And definitely, I think there's still a need for model checking and validation, okay, using instrumented crash tests, okay. We've done a little bit of that. We have some more of that in progress. And before I would want to get out and say, yeah, this is ready for prime time, okay, so give it out to the general public, I'd like to see a little bit more of this crash testing, okay, validation, like what we've shown here so far. So with that, I guess something I forgot to put up here is Acknowledgments. Several people have worked on this. Abhishek Madgal, who is a postdoc, okay, he's not here anymore. He went on to Texas A&M. Miguel Andrews, who was a master's student who graduated a year and a half ago. Jingru Gao, who is in the audience here, has contributed a bit. Christopher Chong, who is contributing now as we speak, okay, with some of this crash testing here. And then I guess in 2016, I took this class called Crash Test Boot Camp, okay, where I learned how to at least start working with this data from crash tests here. And so I got to thank the folks that were on my Crash Test Boot Camp class, okay, who helped with, for instance, that first crash test that we presented here. Okay, give them a shout out as well here. Okay, so with that, okay, be glad to take some questions. Go ahead.
I was to a presentation by General Motors about OnStar several years ago.
Mm-hmm.
And I understand that crash test data that you referred to is downloaded automatically via OnStar for every crash to GM.
From the event data recorders?
From something in the vehicle, they get it via OnStar.
Okay. All right, so GM has it. Okay. All right.
And they've been doing that it was 5 years ago.
Yeah. Whether it's provided to others, that's probably another question, I guess. Okay, all right, but that doesn't surprise me. Go ahead.
Using some of these Bayes statistical models, do you think this is something that could be used in court, or is there too much uncertainty for it to stand up at all, even with an expert such as yourself?
I presented this stuff at the Society of Automotive Engineers conferences a couple of times. And that is, the crash recon sessions are mostly people who do this sort of thing for legal purposes here. And the question I've gotten on occasion, all right, is, well, what good is that to a practitioner? And, the answer is, well, if you want to put a number on your uncertainty, okay, this is how you need to do it. Whether they're interested in putting numbers on their uncertainty in some sort of quantitative manner, I guess that's another question. Okay, I suspect at least some would still like to leave that as more of a rhetorical issue. Okay, who's the jury more willing to believe or something like that. All right, so there's kind of a maybe cautious interest in this, okay, with some at least considering, all right, how does this make my life easier or harder if I were to use it here? You do see papers published on Monte Carlo methods, okay, for assigning probabilities, so they are interested in this sort of thing. I think this is the natural way to advance the Monte Carlo methods that are currently being used, but it gets kind of complicated, okay? Like I say, when I say it's my expert opinion, it's not only my expert opinion about the physics of this, but my expert opinion about correct use, okay, of the computational tools as well here. All right, so we'll see. What we do know, all right, is the National Academy of Sciences came down hard on forensic science, okay, a few years ago because of lack of scientific validation for some of the techniques and inability to determine error rates and stuff like that. So if that ever does become an issue in crash reconstruction, okay, well, here's what we need to do. Yeah.
Sometimes you don't have to be perfect to make a difference. And I know on the way down to Rochester, they have some signs up that say, watch out for crossing traffic, something to that extent. And I can see this being blown up for those intersections where there are left turn errors being made, numerous ones, that engineers would start to say, why don't we sign that the car is too close to go.
Okay. Okay.
Wait, or something like that.
Yeah. I agree. You don't have to be, sometimes you can come to a reasonable decision by just saying, well, I don't know exactly what happened, but probably this guy accepted a really short gap. All right. We can kind of say that in some of these. Okay. Short gap acceptance definitely seems to be present, okay, in the three that we looked at. And then we can go back and ask, why was that? Is it a sight distance issue at the intersection? Is it something funny about the traffic control? Is it the driver was looking at the phone, okay, when they turned? All right, so we can do stuff like say, it looks like short gap's an issue, then why it happens to be an issue in a particular case, that would be the next level, okay, you want to look at.
Thank you.
Sure.
Do you know if in the case of these 3 crashes that you used as an example, they were lighted intersections, in other words, with a stoplight? Because I've been in situations where people, they want to cheat on the yellow light. And I've learned over time to be able to spot that by the dive of the front end when they're braking and when they're not.
That is a really good question. There are, first of all, this NHTSA stuff is supposed to be de-identified. So you're not supposed to be able to tell where they occurred and when they occurred. And if by looking at the photographs and stuff you can figure out where it occurred, then that's an unethical use of that information. I don't want to say for sure, but I know at least one of those, okay, was at a signalized intersection. I have no idea what the signal indication was when the crash occurred. And I'm not sure if one of these, but I know some others in our database are at two-way stop-controlled intersections, okay, where it's definitely permitted left turn, okay, at that event. That's a good point, okay, and it's the nature of these data here that makes it hard, okay, since we are not supposed to know where it occurred and what happened and stuff, you know, like that. We're hard to pin that down. Yeah?
It seems like there's a lot of uncertainty with this EDR. Was that what it's called? EDR?
Event data recorder, EDR, yeah.
It seems like there's a lot of uncertainty in that, but with the development of autonomous vehicles, you have to imagine that they're really monitoring a lot of the things that are happening with the pilot programs that are going on right now.
Mm-hmm.
Do you think the development of autonomous vehicles will give better data in the future for cars, like better EDR or other kinds of recorders?
I think it could, okay. Again, it depends on what the manufacturer decides to store in that buffer, okay, over those few seconds, okay, before the crash occurred. I guess what we know about the crash that occurred down in Arizona here is they did have forward video as well as other stuff, so that's certainly an interesting piece of information in addition to whatever the system was recording here. So potentially, yeah, okay, whether it plays out or not, I don't know. The thing that I took a class in how to use event data recorder information, okay, a couple years ago by a guy who's kind of the guru in this area. And probably the first thing you get when you come away with this is if you were to look at those pre-crash numbers and take those as absolute in of themselves, you're a fool, okay, because there's all sorts of ways that they can misrepresent what's happening, measurement error, lags in between when something happens and when it gets stored in the buffer. And the issues change from model to model and from manufacturer to manufacturer. And so kind of our procedure is, okay, here's the vehicles that are involved. Can we find in the literature some tests that at least give us a rough idea about the uncertainties in these measurements and incorporate those, all right, in our model here. All right, I don't think automated vehicles will make those issues go away. Okay, because they still have to do the fact, you know, is your speedometer an accurate measure of your speed? Well, sometimes, okay, sometimes it's not. All right, if you're on a sheet of ice and you've locked the wheels and you're still sliding forward, your speedometer is going to say 0, okay, but you're definitely not stopped, as an extreme example here. So, you know, as usual, the devil will be in the details.
Can I ask
Yeah.
a question? What if I want to protect myself when I or my spouse or friends are in potential crashes and I want to essentially be able to defend myself from liability issues or be able to say it was not my fault, it was their fault? And I believe you can buy dash cams right now that provide additional data. Is it possible to access the EDR data on one's vehicle and feed that together with the dash cam information, which I'm assuming is GPS and video, in order to be able to do some of these calculations? Is there a standardized system for doing that?
No. All right.
Well,
We're kind of beginners in that area. First I could say is if you are willing to pay the money for the hardware and software, there's probably no reason why you couldn't plug in to your airbag control module and download that data, okay, instead of the cops or whoever else, okay, doing that. So there's nothing to stop you from doing that.
so I can buy that kind
You
of
can buy that.
data acquisition
Yeah,
system? And does anybody sell such things?
Oh, yeah.
No, I mean the dash cam integrated with EPR data access.
Good question. Good question, Max. I don't
Because
know.
now we would know the position, we would know true velocity,
Mm-hmm.
we would know your track, we would have a lot more information.
I conjecture here. Okay, so imagine we got a dash cam, okay, and in addition it's GPS connected. So we can get Greenwich Mean Time, okay, and position, okay. And in addition, we've got the event data recorder down there. The question, all right, can we synchronize those?
Mm-hmm.
If you can synchronize them and then allowing for data lags in the loading of the buffer and stuff, well, I don't see why not.
The one thing that is now recommended with
Mhm.
I think it's the Escort dash cam that I have,
Mhm.
they say to mount it on the dome light
Okay,
so that you are recording the speedometer, steering angle, and forward vision. So you get all three inputs.
so the camera is what, looking down at you while you're driving?
Camera's up here on the dome
Oh,
light.
okay, okay, all right.
So you're getting, because of the wide angle of the
Mhm.
lens, you're getting the speedometer, you're getting the steering angle, and you're getting
Okay,
the forward
All right.
vision. And it's fascinating to see.
I've got a sunroof, so my dome light's like up over the windshield, so I was confused there for a minute, but I know what you mean here.
Yeah.
Okay, all right.
But that's a fascinating thing to see. I've replayed it, and
Uh-huh.
that's a 10-second storage
All right,
with a sampling rate that's literally, I think, 60 hertz.
okay, that's pretty good,
So,
yeah.
they're not cheap, the
Mhm.
dash cams, but
So I guess there's kind of a summary. In terms of monitoring what happens, okay, I guess instrumentation doesn't seem to be a limitation right now. All right, it's probably expense, coordination, okay, as Max was mentioning, okay, and kind of be a brave new world, okay, I guess, as the autonomous vehicles hit the market.
And most crashes are fender benders, so the
Mhm.
cost, how much does the instrumentation cost for a dash cam with all the appropriate access and interfaces and data acquisition, and compare that to your $500 deductible?
Okay, awesome. Okay, so
That.
economics creeping into the issue here. Other questions? All right, I guess we can wrap it up here and start the weekend early maybe, huh?
I take it there were no questions from our audience out in internet land? Okay. Well, thank you all for coming, and I just want to, before we thank Professor Davis for his talk, I just want to point out next week, Thursday, March 29th, the last Thursday of March, we're going to have in-vehicle dynamic curve speed warnings at high-risk rural curves presented by Brian Davis. So that's next week, same time, same place. Again, in-vehicle dynamic curves. I believe, if I remember correctly, they collected a lot of data with rural drivers at various rural curves in order to figure out when do people slow down or don't slow down at these dangerous curves. So again, next week, same time, same place. And please join me in thanking Professor Davis for a very interesting talk. Thank you all for coming.
All right, I'd say that one next week sounds interesting.
Well, please.
Yeah. Yeah, well, I think I've got it in my emails here, but yeah. I've got it in my calendar too. Whether we pull it off or not, that's the question here.
should I ask you?
extension of providing a paper, PhD qualification.
Oh,